recall once again that the one-dimensional wave equation which we have been using thus far had the following form: d2f by dx2 minus 1 over v square d2f by dt2 is equal to 0. So this one-dimensional form of the equation essentially is a scalar equation because f, the primary input to this equation, is a scalar function of x and t, that is, it's not a vector. Now, if one were to rigorously ask this question, how do we know that light is a wave and an electromagnetic wave? Then we ought to pause. If one were to now ask this question as rigorously as we can and say, how do we know that light is an electromagnetic wave? Can I establish this from first principles, from the known laws of nature as physics informs us today? Then of course we cannot start from the fact that waves are described by this equation, propagating waves are described by this equation, and that if I replace f by e as we did earlier, that's a propagating light wave. How do we even know that this is the governing equation for light waves, right? So this indeed was a matter of um, important physics discussion historically, so much so that one might even call this a substantial revolution in physics, in which two people, at least two people, played a very important role. And in fact, one of them is the famous James Clerk Maxwell, after whom this enormously important set of equations describing electromagnetic phenomena in physics, that is, Maxwell's equations, are named. And going further, that being the theoretical framework, another important physicist established this from the perspective of experiments in physics. So let's look at this question in some detail, right? So we will explore the notion that light is made up of electric and magnetic fields. It's an electromagnetic phenomenon. The fact that they come together to form light waves by examining these iconic equations, which are in themselves an edifice in the framework of physics, right? So Maxwell's equations, written down for in fair amount of generality using electric and magnetic fields in a medium with permittivity epsilon and permeability mu, under the assumption that in the medium of consideration there are no free sources, that is, there are no free charges or currents. The most general form of Maxwell's equations, we can write them down so as to include free sources, that is, charges and currents. But in the case of optics, media that we concern ourselves with often or almost always do not have free sources. We actually treat scenarios in such a way that the source is treated separately from the propagative phenomena, right? This works for optics in a very nice way and simplifies matters a lot. So let us take this way of writing Maxwell's equations down. The first equation, in which is the divergence of the electric field, in this case, because there is no free charge, is 0 on the right hand side, is the Gauss law for electric fields. Then we have the corresponding equation for magnetic fields, which is the divergence of B is equal to 0, right? So this is true always since there are no magnetic monopoles. So we also learn this in courses on electrodynamics as the Gauss law for magnetic fields. And then we have Faraday's law, which is del cross E, or the curl of E, is equal to minus dB by dt, right? This is Faraday and the electromotive force, EMF, and so on captured in it. And the last equation, curl of B, that is del cross B as it is written here, is equal to mu times epsilon multiplying dE by dt, the partial derivative of the electric field with respect to time. This is Ampere's law. Right. In the case where we have free currents, we would have had essentially an additional term here on the right hand side as J, the current density with the subscript f, Jf, which happens to be 0 in this case. Okay. So these are the four Maxwell's equations that describe an electromagnetic phenomenon in a medium with permittivity and permeability of epsilon and mu without any free sources. Okay. So now with a little bit of math, which we will leave as an exercise for the student here to prove using vector calculus, we can show that from these four equations for the context of no free sources essentially boil down to this wave equation. While I will not write down and do the math for the whole solution, I will just indicate to you as to how we can go about doing this, right? So consider this equation, Faraday's law, the curl of E is equal to minus dB by dt. Now let's add another curl. Let's take the curl of E on the left hand side of Faraday's law and take identically the curl of the right hand side. Then do the following. Substitute for the curl of B over here with the time derivative of E. Then write down curl of E to be a certain a certain vector calculus identity which involves the Laplacian, that's del squared, and it will also involve a term where we take the gradient of the divergence of E. Since the gradient of the divergence of E is 0, only the Laplacian term survives, and then we are at this result. So we leave this as an exercise for the interested student. Now the point is that Maxwell essentially unified what hitherto was viewed as two separate components of physics, the physics of electric phenomena and the physics of magnetic phenomena. Michael Faraday showed that a time varying magnetic flux induced through a loop induces a current, right, and so on. So there was a strong indication at that point that electric and magnetic phenomena are somehow interrelated or interchange in a particular way. They can sort of exchange roles even. But then these four laws were named after three giants in physics, essentially were put together and unified by Maxwell into one framework of electromagnetics, and this is often called the first unification in physics, a first sort of unified theory where two apparently independent or unrelated pieces of physics were put together in a tight mathematical framework. Immediately as a consequence of that, Maxwell realized that electric and magnetic fields can combine to form in a form that becomes the wave equation. I should also mention here that identically in the same process and the same scenario, one can deduce a corresponding equation for the propagation of magnetic fields, and therefore light becomes an electromagnetic propagating wave. But we are somewhat biased towards describing light as an electromagnetic wave, but writing it down only in terms of its electric field for good reason, which is true for most media, but something which we will sort of elucidate better in later discussions. But having done this, right, we still need to prove that this is a propagating electromagnetic wave in an experimental lab, because in one sense physics is an experimental science. It's a science of observation, meticulous experiment and theory all playing themselves out together at their best on the playground of nature. So the experimental, if you wish, the verification of this, of Maxwell's prediction, was done by Heinrich Hertz in Karlsruhe in Germany. So early on these were called Hertzian waves. And here is maybe a little tidbit of information which goes on to make the point that fundamental science essentially goes over and pays itself over many times. From the perspective of being applied, we have electromagnetic waves all around us, all these devices. In fact, the fact that this lecture is being recorded at some point or communicated at some point involves electromagnetic phenomena through and through. Even the audio is captured using microphones which finally are electromagnetic in nature. The camera that records is electromagnetic. The internet cable that carries this information is electromagnetic. The storage device, wherever it is very likely magnetic, and so on. So therefore these phenomena pervade us. And if one really thinks about this little piece of history, when Hertz apparently discovered is the fact that these are Hertzian propagating electromagnetic waves, he was questioned whether he foresaw any applications of the phenomenon that he observed. And at that point, apparently Hertz commented that there will probably be no application of this. But today we know that these are all pervasive and even empowering technologies in our hands. So that's maybe a little lesson in how basic science or fundamental science goes on to become the mother of transformative technologies in the history of humankind. That aside, light is an electromagnetic wave, and the electric field is a vector quantity in 3 dimensions. So we should have vector signs everywhere where they belong. Also over the temporal derivative, so let me just correct that spontaneously. Now, repeat, pause, resume. That said, electric fields are fields of 3-dimensional vectors, right? So therefore the wave equation which we derive in its complete physical form is a 3-dimensional propagation equation of the kind that we have been concerning ourselves with so far. So these are very importantly 3D, and the solutions also must be 3-dimensional in nature. So if we now write the 3D wave equation in Cartesian coordinates, these should be d2e by dx2 plus d2e by dy2 plus d2e by dz2 minus mu e multiplying d2e by. But moving on, electric fields are 3-dimensional real quantities. The wave equation they are described by, in the case of propagating waves of electromagnetic nature, also are 3-dimensional equations. So the 3-dimensional wave equation turns out to be del square E minus mu epsilon d2E by dt2 is equal to 0. Now in Cartesian coordinates we can write this down as d2E by dx2 plus d2E by dy2 plus d2E by dz2, where x, y and z or z are the spatial variables for 3D space, minus mu epsilon the permittivity and permeability. Their product multiplies d2E by dt2 is equal to 0. This has the solution. E, once again we use the tilde underneath to denote the fact that this is a complex quantity, or we are using the complex notation, electric fields are not a complex quantity, they are a real quantity in terms of their physical nature. E tilde of x, y, z and t, 3 spatial and 1 temporal variables, is equal to E naught of tilde, the complex amplitude which contains the product of the real amplitude, and e to the I theta, the complex the complex number in its polar form, where theta is the initial phase, multiplying this the part that oscillates fast and enables the propagation, which is exponent of I k dot r minus omega t, right. Here, while the angular frequency omega is still a single scalar quantity, k has 3 components, one corresponding to x, one corresponding to y, the third corresponding to z, as the case is from this expansion of the Laplacian del squared, right. So, k is then a vector with 3 components, kx, ky and kz per definition. By definition, it has 3 components, it is a vector. In a different coordinate system, let us say spherical coordinate system, this would have been kr, k theta, k phi, if r theta and phi are the descriptors of the spherical coordinate system, or perhaps for any other. The position vector that we are concerned with here in the Cartesian case is r. R has x, y and z to be the 3 spatial coordinates. K dot r is kxx plus kyy plus kzz. This is the spatial part of the complex exponent in the argument, whereas k squared is kx square plus ky square plus kz square. So, this brings us to now a nice wrap around that light is a propagating 3-dimensional electromagnetic wave whose electric and magnetic fields follow, in this case of light propagation, the wave equation, which is described here in the top right corner, and its solutions can be written down using primary functions which have a sinusoidal form, and they can be written further in terms of the complex notation as E of x, y, z, t is equal to E naught exponent of I k dot r minus omega t. So, this is a nice point to take a pause and sum things up. We looked at waves, we looked at one-dimensional generic waves, we looked at one-dimensional light waves, and wrote down the one-dimensional wave equation for 1D waves and 1D light waves, their most elementary solutions in the form of sinusoidal functions, and then realized that the wave has an amplitude, a spatial period, a temporal period, wavelength, time period, then wave vector, angular frequency, cyclical frequency or frequency, and an initial phase. And we then realized that we can write this down in terms of complex notation, which we can exploit in summing up waves or forming their superposition. And when waves have the same frequency but then have different initial phases, they can rather easily be summed up using the complex notation. And then we took the primary equations of electromagnetism, which is Maxwell's equations, in the context of having no free sources or currents, but in a material medium or vacuum as the case may be, and figured that from these equations it becomes deductible that electromagnetic phenomena can lead to propagating electromagnetic waves whose fields, electric or magnetic fields, which are real, can combine themselves to form an electromagnetic wave, and each of these vector fields essentially then obeys a 3-dimensional wave equation, as in this case has been written down for the electric field, and setting a coordinate system to its context, here being Cartesian, we can write down its solution once again in the form of a harmonic sinusoidal wave, where we have E x y z t is equal to E naught exponent of I k dot r minus omega t, where k is the propagation vector with 3 components kx, ky, kz. R is the position vector in x, y, z and t, and that sums up the fact that light is an electromagnetic wave, and we have set up the framework for further exploring electromagnetic waves of optics, photonics and attosecond science and technology. Thank you. With that, this lecture closes.